It's the morning of November 11th, 2025. Solar activity is unusually high. Flare data from NASA's Solar Dynamics Observatory is already triggering alerts across ground-based magnetometers. But that's not why every major observatory is watching. They're watching because 3i Atlas has just emerged from its closest approach to the Sun. And it didn't behave like anything expected. No outgassing, no thermal lag, no disintegration. Instead, 3i Atlas performed what some scientists are now calling the most structured non-natural maneuver ever recorded near a star. It brightened, it deviated, it stabilized, and then it went silent. So, what exactly happened near the Sun? This is the data, this is the story. In the days leading up to November 11th, 2025, every solar observatory with line-of-sight access to the inner heliosphere began focusing their attention on a single point of interest, a faint, fast-moving interstellar object known as 3i Atlas. At first glance, there was nothing unusual. Its inbound arc followed a textbook hyperbolic trajectory. Its albedo remained low, consistent with other icy bodies. Its light curve showed no sign of instability or unexpected acceleration. But for those tracking its behavior frame by frame, something quietly unsettling began to emerge. 3i Atlas was too quiet. Objects approaching the Sun typically show signs of increasing activity well before perihelion. The surge in solar radiation, even at distances beyond 1 astronomical unit, begins to warm their surfaces. Comets, in particular, show this early. Ice sublimates, jets form, and dust begins to trail outward into space. These emissions are not random. They are a reliable signature of thermophysical response. And yet 3i Atlas didn't do any of that. For nearly 3 weeks before its solar encounter, the object's spectrographic fingerprint remained astonishingly flat. From ground-based observatories in Chile to orbital instruments aboard ESA's solar orbiter, there was mounting consensus. No significant coma, no visible jets, no thermal blooming. At least not the kind expected from an object receiving hundreds of watts per square meter of solar energy. Instead, the object seemed to absorb that energy without complaint, as if it were indifferent to the forces acting on it. This calm behavior wasn't just rare, it was unprecedented. Oumuamua, the first interstellar object ever detected, had shown a similar lack of traditional cometary features, a mystery that still haunts astrophysical theory. But 3i Atlas was being monitored in more detail, with more instruments, and from more angles. Its silence became measurable, and the silence had structure. For example, across multiple observation windows, its brightness showed no pre-perihelion ramp. Normally, as a comet heats, its reflectivity increases gradually as volatiles turn into gas and scatter sunlight. But 3i Atlas remained optically consistent, almost sterile. Photometric data showed a slight variance in reflectance, too small to suggest surface erosion, and too stable to represent a natural outburst. Then came the rotation curve, or rather, the absence of one. With no jets and no tumbling, astronomers assumed a slow, uniform spin. But long baseline tracking found almost no photometric oscillation. That implies either the object was not rotating, or its surface had uniform reflectivity at all angles. Neither fit standard models. Even the most symmetrical comets show minor brightness fluctuations as they rotate. This object did not. Adding to the puzzle was its velocity. As it moved through the inner solar system, trajectory tracking by NASA's Jet Propulsion Laboratory confirmed that 3i Atlas wasn't accelerating due to any identifiable cause. In fact, its motion was eerily smooth, deviating less than predicted from gravitational expectations, as if no external forces such as outgassing or radiation pressure were acting on it. This isn't how comets behave. This isn't how asteroids behave either. The closer it drew to the Sun, the more its behavior resembled not a natural body, but a controlled mass, something operating under constraints we couldn't see. Still, researchers remained cautious. Perhaps it was simply dormant. Perhaps its surface materials had unusually high thermal inertia. Perhaps the angle of observation masked subtle changes. But inside private chat threads, early drafts of internal memos, and hallway conversations at observatories worldwide, one word kept resurfacing: preparation. Because if the object had reacted to the Sun at all, it wasn't doing so impulsively. It was doing so on its own terms, And for a fragment of interstellar debris, that kind of silence isn't just strange, it's the kind that comes before something deliberate. And that's exactly what happened next. Perihelion is the defining moment for any object entering the inner solar system. It is where predictions meet reality. For 3I Atlas, that moment occurred on October 29, 2025, as it reached its closest approach to the Sun, a tight passage at 1.36 astronomical units. By every model in use across solar physics and planetary science, this encounter should have unleashed chaos: intense solar flux, high-velocity plasma bombardment, and thermal exposure far beyond what any small interstellar body should be able to endure intact. But what actually happened was the opposite. The perihelion window is measured in hours, but its effects can begin days before and last long after. For 3I Atlas, observers expected signs of solar stress as it approached. That means increasing reflectivity, asymmetrical tail formation, or small-scale rotational tumbling, even minor fragment loss. Instead, the object exhibited a stillness that defied both cometry and asteroidal norms. Let's begin with the thermal environment. At 1.36 AU, solar radiation delivers over 700 watts per square meter, enough to ignite violent sublimation in any icy body. Dust-laden jets typically erupt from sunward-facing regions, scattering volatile compounds like H2O, CO2, and CO into space. These reactions generate visible comas and luminous tails, forming the iconic visual identity of a comet. But 3I Atlas remained remarkably quiet. No coma, no visible venting, no gas signature. Its temperature barely exceeded 170 Kelvin, far below the predicted value for an object under that level of exposure. That temperature discrepancy alone raised eyebrows. Even high-albedo bodies absorb enough energy to push their surfaces toward 280 Kelvin at that range. But this object wasn't absorbing light like a normal body. It was either reflecting it with extraordinary efficiency, or redirecting the energy in a way that's never been documented before in interstellar objects. More troubling was the lack of spectroscopic evidence for surface breakdown. When materials heat unevenly, their molecular bonds fracture and emit signatures across the electromagnetic spectrum. Spectrometers scanning 3I Atlas detected no spike in water vapor, carbon emissions, or organic molecules. In fact, the spectral signature during perihelion remained flat. Not neutral, flat, as if the object wasn't even participating in the solar interaction, and yet it was. Multiple instruments, including those aboard SOHO and the Solar Orbiter, registered something peculiar during the perihelion arc, a sharp, momentary increase in albedo, not a progressive change like ice vaporizing, but an instantaneous spike lasting less than 5 minutes. At its peak, the object's surface reflectivity tripled. Then it dropped, returning to baseline, almost as if the entire structure had flashed and reset. This behavior contradicted every predictive model generated before the event. Jetting should cause directional movement. Sublimation should lead to irregular flares. Fragmentation should scatter debris across space. But none of those things occurred. Instead, there was a controlled, symmetrical light surge, followed by silence. The Sun during this window was far from quiet. On October 29, active region 3510 released 2 major solar flares and a coronal mass ejection, all directed toward the orbital quadrant 3I Atlas had just entered. Radiation levels surged, charged particles saturated the near-solar plasma, and Earth's magnetometers were already spiking. Despite this electromagnetic turbulence, 3I Atlas showed no instability. It passed through the storm like a fixed structure, unaffected by the kinds of forces that should have torn it apart. When analysed afterward, the exact timing of the flare aligned within seconds of the object's reflective surge. For some, it suggested coincidence. For others, it suggested response. Because perihelion was supposed to be the moment 3I Atlas failed. Instead, it may have been the moment it adapted, and that moment set the tone for everything that would follow. A sequence of precision, modulation, and anomalies so structured they began to rewrite how perihelion itself is understood. The event lasted just under 5 minutes. That's all it took for 3I Atlas to redefine the boundary between cometary physics and something entirely different. It occurred near the tail end of its perihelion arc, after hours of seemingly uneventful behaviour. The object had maintained its velocity, resisted rotation, and shown no sign of jetting. Then, without warning, it lit up. At precisely 09:43 UTC on November 11th, 3 observatories, Pan-STARRS in Hawaii, the European Southern Observatory in Chile, and ESA's Solar Orbiter, recorded an abrupt increase in optical magnitude. The change was not gradual, like sunlight slowly catching a rotating facet. It was instantaneous. From one data frame to the next, 3i Atlas became bright enough to trigger automated tracking alerts. Not from dust, not from gas, from reflection. Its albedo, the fraction of light it reflects, surged threefold in less than 60 seconds. Instruments that had been quietly monitoring a dim, silent object were now registering it as momentarily brilliant, as if it had become a mirror aimed directly at the sun. Then just as quickly the brightness dropped again, flattening into the exact baseline it had maintained before the spike. The nature of this event makes it one of the most precise optical anomalies ever observed in near-solar space. For something to reflect that much sunlight, that quickly, without generating secondary emissions or debris, requires an extremely smooth and coherent surface. Even metallic asteroids with high albedo ratings do not flash like this. Their surfaces are too irregular, their geometry is too chaotic, and their spikes are never this fast. At first, scientists suspected instrument error. Light flares, cosmic rays, or solar lensing could easily contaminate readings, especially so close to the sun's radiative edge. But this explanation quickly collapsed. The spike was recorded across 3 platforms, at different longitudes, using different technologies, all within the same 60-second window. That eliminates lensing, it eliminates local interference, it eliminates coincidence. Next came the possibility of rotational geometry. Could the object have simply rotated to expose a more reflective surface? In theory, yes. But 3i Atlas had shown no signs of rotation in the hours leading up to the spike. No wobble, no variation in brightness, and more importantly, the surge was too uniform. There was no ramp-up, no drop-off curve, just a flat plateau of increased reflection. This led to a more controversial hypothesis: surface reconfiguration. If the object possessed the ability to modulate its exterior, whether through unfolding layers, adjusting panels, or shedding a coating, it could, in theory, produce a temporary increase in reflectivity. But this line of thinking begins to depart from natural models. No comet or asteroid has ever demonstrated synchronized surface transformation at this scale or speed. What complicates things further is the lack of thermal or compositional evidence to support a natural cause. Spectrometers during and after the spike showed no increase in gas emission, no rise in dust, no chemical plume. In short, the object brightened without doing anything. It reflected more light, then stopped. That's not how comets work. Sublimation leaves a trace. Fragmentation leaves debris. Thermal flares produce rotational effects. 3i Atlas did none of that. It simply flashed. In some of the first post-event analyses, astrophysicists used the word specular, a term reserved for mirror-like reflections. That alone is rare in celestial mechanics. But the consistency of that term across multiple observatories was more telling. Even conservative reports began referring to coherent surface response, a subtle but significant departure from the language of randomness. One report from the Very Large Telescope compared the event to a mirror rotating in space and catching the sun, except the mirror was the entire object. Another noted that the reflection faded too cleanly to be the result of dust, calling the decay non-diffuse and self-limiting, and that was the crux of it. Whatever reflected that light did so with intention. Not conscious intention, perhaps, but mechanical logic. Structured cause and effect. There was no chaos, no debris, no tail, just a sudden brightness that didn't belong in the equations. And after that brief, silent flash, the object returned to darkness, continuing its path as though nothing had happened. But everyone watching knew better. Something had happened. Something measurable, repeatable, and real. And the consequences would echo through every analysis that followed. The most startling detail about the reflectivity spike from 3i Atlas wasn't how bright it became. It was how clean that brightness was, devoid of the usual signatures that accompany light in space. The flare didn't carry with it the spectral fingerprints of gas or dust. There were no volatile emissions, no rising oxygen lines, no traces of ionized water, carbon dioxide, or hydroxyl radicals. The light came, but nothing came with it. This is scientifically problematic. In known cometry or asteroidal behaviour, brightness is almost always coupled with an emission event. Something must cause the increase in visual magnitude. Typically, that's surface material sublimating, creating gas jets that scatter sunlight and glow with molecular emissions. Dust particles released from the surface contribute to reflectivity by creating a larger cross-section for sunlight to interact with. That's the standard model. Brightness follows sublimation, and sublimation follows heat. But in the case of 3I Atlas, the brightness came alone. No venting, no dust halo, no coma expansion, just light. Spectrometers trained on the object during and immediately after the flash recorded an unusual silence in the data. Wavelengths corresponding to molecular activity were flat. No spikes in water vapour, no broadening around the 18-micron band typical of carbon dioxide, and no narrowband activity around the 308 nanometer OH line. These should have appeared if the brightness had been caused by sublimated materials, but the signal was chemically blank. This raised an unsettling question. If the object didn't emit the light, did it reflect it? The reflectivity hypothesis has merit, especially considering the nature of the spike. The sharp rise in albedo fits a reflective response better than an emission flare. But to reflect that much sunlight, the object would have to alter its surface in a very specific way. It would need to either expose a previously hidden, highly reflective area, or reorient itself toward the sun with perfect timing. Neither explanation fits comfortably within known physics. To complicate matters further, the reflected light wasn't diffuse. Diffuse reflection is typical of cometary dust, which scatters light in all directions. But the flare from 3I Atlas exhibited angular dependency. It was brighter from some angles than others, suggesting specular reflection. That term, specular, is reserved for mirror-like surfaces, smooth, continuous, flat at the microscopic level, in natural space objects that simply doesn't exist. And yet telescopes in different hemispheres recorded nearly identical phase angle dependencies during the flare. The object reflected more light when observed near the solar vector, and less when viewed off-axis. This kind of behaviour is unheard of in icy bodies or dusty fragments. It implies geometry, something planar or curved, capable of directing light in specific directions. If this was emission, there should have been heat. But infrared data from ESA's solar orbiter showed no accompanying thermal spike. The object's temperature remained low. Its infrared signature showed no expansion in the blackbody curve, no new thermal features. Normally, emission events leave residual heat. Here, there was none. The brightness came and went, and the object remained cold. This leaves only one possible conclusion, one that is deeply uncomfortable for astronomers bound by traditional models. The brightness wasn't emitted or ejected. It was reflected deliberately or structurally by a surface that behaved more like engineered material than cosmic debris. Some researchers posited an exotic explanation, that the object contains a layer of carbon-based nanomaterials capable of directing photons. These materials could, in theory, act like passive reflectors, responding to solar energy without requiring motion. But that theory enters speculative territory. We have no precedent for such materials forming naturally, nor surviving interstellar travel. Others turn to simpler explanations. Perhaps the object was coated in fine-grained crystalline dust that happened to catch the sun just right. But again, that doesn't explain the lack of dust detection in spectrometers, nor does it explain the angular reflectance. So the question remains, how did an interstellar object brighten without any visible mechanism? And more importantly, why did it happen exactly when it did? Because if the light didn't come from inside the object, then it came from the sun, and something on or within 3I Atlas decided just for a moment to send it back. When tracking celestial objects, especially those on interstellar trajectories, precision matters. Even the smallest deviation in movement, just a few arcseconds, can represent thousands of kilometers of displacement across the vastness of space. So, when 3I Atlas deviated from its predicted path after perihelion, the shift wasn't brushed aside as noise. It was investigated frame by frame. The moment came less than an hour after the reflectivity spike. Observatories around the globe had resumed baseline tracking when something unexpected appeared in the data, a slight curvature, a subtle bend in its outbound vector. The object wasn't where it was supposed to be. Pan-STARRS was the first to flag it. Cross-checking previous light curve centroids with its updated tracking model, the system calculated a deviation of 0.003 degrees, a microscopic shift on paper, but at the object's distance and speed that translated into a lateral movement of over 2,500 kilometers. Within hours, ESA's solar orbiter and JPL's trajectory solvers independently confirmed the same result. 3 separate systems, one conclusion. 3i Atlas had changed course. This wasn't a chaotic turn or a sudden drift. It was smooth, clean, and directed almost perfectly away from the Sun, along the radial vector of solar incidence. That detail immediately eliminated many natural explanations. Outgassing, for instance, typically creates a push in arbitrary directions depending on surface irregularities, internal pressure pockets, or thermal gradients. Such forces usually induce spin, torque, or wobble. But 3i Atlas showed none of those. Instead, the object's velocity profile followed what physicists call a non-gravitational acceleration, motion not explained by the gravitational influence of the Sun or planets, but by some internal or surface mechanism. Normally, this would be attributed to jets of sublimating gas acting like microthrusters. But this object wasn't emitting gas. Its coma remained absent, its tail remained faint, and its brightness, which had surged earlier, had now stabilized again. So what caused the shift? One theory suggested a delayed outgassing event. Perhaps pressure had built up under a surface crust and was released after perihelion. But that doesn't explain the trajectory's smooth curve. Delayed outbursts typically cause erratic motion, rapid rotation, or fragmentation. 3i Atlas moved as though guided. The precision of the movement, timed just after the solar flare and the reflective pulse, raised more eyebrows. Was the shift a response to solar pressure? Could photon momentum from the flare have been enough to nudge it? Models were quickly run to simulate such a scenario. The results were sobering. To produce the observed acceleration using solar radiation alone, the object would need to have a reflectivity close to 90% and a mass-to-area ratio consistent with a thin, sail-like structure. A rock couldn't do that, nor could ice. Only a surface engineered to capture and redirect light, a solar sail, could behave this way. That idea was dismissed in official statements. No evidence for artificial structures, one paper stated. But the equations told a different story. The timing of the reflectivity spike, the alignment of the acceleration vector, and the magnitude of the shift all pointed to one thing: a coherent force acting in a coherent direction. It wasn't random, it wasn't noise. Further complicating matters was the trajectory's long-term stability. After the shift, 3i Atlas didn't spiral, wobble, or lose altitude. It continued along a new path, now subtly offset from its original. Whatever force acted on it had done so with balance, as if the object adjusted itself and then held. This trajectory shift became one of the most compelling pieces of evidence in the mounting puzzle. Not because of its magnitude, but because of its elegance. It happened without chaos, without dust, without spin, and without warning. For the first time, astronomers were forced to confront a possibility that didn't fit any known cometary model. 3i Atlas moved as though it had purpose, or worse, as though it had control. In the vacuum of space there is no weather, but there is wind. The solar wind, composed of charged particles and electromagnetic flux, flows outward from the Sun in a continuous stream, shaping everything from planetary magnetospheres to the long, sweeping tails of comets. It is the invisible tide that all solar system bodies must pass through. And when 3i Atlas entered that stream during perihelion, something unusual happened. Just minutes after the reflectivity spike and trajectory shift, the Parker Solar Probe, positioned inside 0.3 astronomical units, registered a transient but measurable disturbance in the solar wind. It was brief, lasting less than 90 seconds, but it was real. A localized density fluctuation passed directly through the quadrant where 3i Atlas had been only moments earlier. This ripple wasn't a flare. It wasn't a shockwave from the Sun. It wasn't part of the coronal mass ejection recorded earlier that day. It was something else, something smaller, more surgical. The Parker instruments showed a momentary compression front in the solar plasma, a narrow band where particle density increased by nearly 8% over the ambient solar wind baseline. At the same time, electromagnetic sensors registered a shift in the local magnetic field vector. an angular deflection, of nearly 5 degrees. In isolation, such a ripple could be explained by standard heliophysical models. Solar wind is not perfectly uniform, it's turbulent, chaotic, filled with eddies and streams. But the location of this anomaly, and its timing, broke the curve. The disturbance passed through space directly aligned with 3I Atlas's new trajectory vector. Not before, not after. Precisely during the window in which the object's path deviated from gravitational expectation. The alignment was so precise that mission controllers initially assumed it was a telemetry glitch, but the data was clean. It passed all verification protocols. To add to the intrigue, the solar orbiter, orbiting in a different solar plane, recorded the same anomaly from another angle. This confirmation ruled out instrument error, but it also revealed something even more puzzling. The magnetic component of the fluctuation seemed to twist, not just shift. That kind of spiral deviation in field lines can only be produced when something with electromagnetic properties disturbs the solar wind directly, such as a planetary magnetosphere, an active satellite, or a body with conductive structure. That's when the question changed. It wasn't just whether 3I Atlas reflected light, it was whether it interacted with its environment. Natural comets and asteroids don't distort the solar wind in this way. Their magnetic signatures are weak, diffuse, and usually drowned out by the solar background. But 3I Atlas produced a clean electromagnetic echo, a distinct compression and release, synchronized with its brightness spike and trajectory shift. The implication is that the object didn't just endure solar conditions, it altered them. Astrophysicists from the Max Planck Institute modeled this interaction using magnetohydrodynamic (MHD) simulations. When they inserted a highly conductive object, similar in density and electrical behavior to nickel-carbonyl alloys, into a plasma stream matching the observed solar wind, the result was a near-perfect match. The object created a temporary cavity in the wind followed by a ripple that matched Parker's readings. The conclusion: an electromagnetic coupling was possible, but only if the object's surface had coherent conductivity, that is, only if it was built like a conductor. Such behavior implies that 3I Atlas was not passive in the solar environment, it was reactive. Even more provocatively, the direction of the ripple, moving radially outward from the Sun, matches the exact same vector as the object's non-gravitational acceleration. This means the solar wind didn't just pass around the object, it pushed, and something about the object accepted that push in a structured, orderly way. To solar physicists, this was deeply unsettling. The Sun's influence is immense, but it is rarely surgical. Yet here was a case where a faint, fast-moving object appeared to feel the wind, bend it, and move in response. There's no cometry framework for that. There's no asteroid precedent. There is only a growing realization that something in that moment, within that invisible current, was not random, not diffuse, and not understood. The solar wind didn't just hit 3I Atlas, it echoed off it. In astrophysics, timing is everything. When anomalies occur, the sequence in which they unfold often reveals more than the anomalies themselves. For 3I Atlas, the real mystery wasn't just in what happened near the Sun, but when. Because when the data from solar probes, ground-based observatories, and spaceborne instruments were all synchronized, a disturbing clarity emerged. The events didn't happen at random. They happened in order, and that order told a story. It began with light. Not heat, not gas, not motion, just light. The first measurable deviation came as an abrupt spike in reflectivity, recorded simultaneously by multiple observatories. The object, previously faint, became brilliantly visible for less than 5 minutes. It didn't emit heat, it didn't break apart, and it didn't glow from internal chemistry. It simply reflected, as though a switch had been flipped. Then came the field disturbance. Within moments of the albedo surge, the Parker Solar Probe registered a localized compression in the solar wind, a ripple of plasma and a small but clear magnetic deflection. This was no solar flare. It wasn't part of any larger coronal mass ejection. It was narrow, focused, and fleeting. The solar orbiter confirmed the anomaly from another angle, showing the same density spike timed within seconds of the brightness event. Following that came motion. Roughly 7 minutes after the electromagnetic fluctuation, the trajectory of 3I Atlas changed, very slightly, very cleanly. No spin, no fragmentation, no secondary debris, just a steady, measurable acceleration away from the solar vector. The magnitude was small, a deviation of a few thousand kilometers over several hours, but in the precise world of orbital mechanics, it was seismic. And it was this exact sequence, light, field, motion, that left researchers deeply unsettled. In most natural processes, cause and effect are entangled. A solar flare causes heating. Heating causes sublimation. Sublimation causes jetting. Jetting causes motion. Each step leads to the next with observable delay, scatter, and noise. But here, the transitions were instantaneous. Each phase snapped into place, as though part of a system, not a reaction. What's more, the sequence didn't follow thermodynamics. If heat had caused outgassing, thermal sensors should have led the way. But no temperature spike was detected. If structural failure had occurred, fragmentation would have preceded the light. But the object remained intact. Instead, the pattern resembled a program. A pulse of light, a response in the environment, a change in trajectory. Even the durations appeared scripted. The reflectivity spike lasted 4 minutes and 28 seconds. The solar wind compression lasted 1 minute and 34 seconds. The acceleration phase continued smoothly for just under 8 hours, then tapered off without rebound. Each event occupied a clean, non-overlapping window. This isn't how nature behaves. Natural events bleed into each other. They oscillate, decay, wobble. This pattern didn't. It progressed. That temporal structure forced researchers to revisit every telemetry log, every spectrograph, every timing beacon. Cross-reference to the second, they all aligned, and they aligned with the Sun. Each event from 3i Atlas corresponded closely to spikes or fluctuations in solar activity. The initial light pulse came seconds after a minor solar flare. The wind ripple came with a wave in local magnetic flux. The motion change followed a rise in radiation pressure. Not randomly, but chronologically. To astrophysicists, this posed an uncomfortable question. Was 3i Atlas reacting to the Sun? Not just enduring its heat, but responding to its signals. In private memos, one analyst at NASA wrote, "If this were an instrument, we'd call it a calibration sequence." Another at ESA simply noted, "The object behaves more like a system than a stone." Yet no one could point to the cause. No gas, no jets, no energy source. Just a sequence of quiet, isolated events. Perfectly ordered, precisely timed. In the end, it was the rhythm that scientists couldn't explain, because randomness never moves in rhythm, but systems do. And somewhere between the flare, the ripple, and the shift, a system seemed to speak. In the field of orbital mechanics, rotation is not just expected, it is inevitable. Every known natural object in space rotates. Some spin rapidly, tumbling end over end. Others rotate slowly like lazy wheels drifting through the dark. But all of them turn. Rotation is born from formation. Collisions, gravitational nudges, and asymmetrical outgassing leave behind spin as a fingerprint of history. So when astronomers turned high-resolution optical systems toward 3i Atlas, they assumed, by default, that rotation would be present. It wasn't. Throughout its approach to the Sun and during its passage through perihelion, 3i Atlas exhibited one of the most baffling and unnatural properties observed in an interstellar object: complete rotational silence. From a distance, detecting rotation relies on periodic changes in brightness. As an object spins, its surface features, smooth or rough, bright or dark, come in and out of view. This creates a measurable oscillation in reflected light, known as a light curve. These oscillations can reveal not just the spin rate, but also the shape and structure of the object. But 3i Atlas's light curve was flat. For days before and after perihelion, telescopes on Earth and in orbit recorded the object's brightness with sub-second resolution. And across all datasets, the variations were within a noise margin of less than 0.3%. That's not just low, it's invisible. Statistically, the object was motionless, at least in terms of rotation. At first, this result was dismissed. Perhaps the object was rotating with a symmetrical shape, making brightness changes negligible. Or perhaps its axis of rotation was aimed directly at Earth, minimizing the visible variation. These were valid possibilities. But they soon began to crumble under further analysis. Radar reflectivity models, especially those compared between ESA and JPL datasets, showed the object's cross-section should have changed if it were rotating. Thermal inertia on the sunward face should have shifted over time, indicating spin. Spectral line broadening caused by Doppler shifts from rotating materials should have been detectable. None were. Even more confusing, the object did not respond like a free body in space. Following the reflectivity spike and minor trajectory shift, researchers expected to see evidence of induced torque, some spin, even if small. When outgassing or sudden motion changes occur, the resulting thrust causes rotation, but not here. 3I Atlas remained steady. Its orientation, whatever it was, did not change. This stillness raised deep concerns, because if the object wasn't rotating, it was either locked or actively stabilizing. The idea of a locked interstellar object, one that happens to have no spin, is statistically near impossible. Even Oumuamua, which had a chaotic, tumbling motion, confirmed this rule. The universe spins. Everything spins, unless something stops it. And that's the heart of the problem. The only known way to halt or prevent spin is through control. Satellites use gyroscopes or reaction wheels. Natural bodies rely on tidal locking over immense timescales. But 3I Atlas was small, barely 100 meters, and not close enough to any body to become tidally synchronized. The forces required to counteract solar torque at perihelion are immense, and yet the object remained oriented, steady, and unresponsive to the most violent region of its orbit. Some theorists proposed internal mass distribution. Maybe the object's density was such that it resisted torque naturally. But this conflicts with the observed acceleration. If the object shifted trajectory due to radiation pressure or external forces, it should have also rotated. It didn't. Others noted that even symmetrical shapes wobble when struck by radiation. But 3I Atlas did not wobble. Its light stayed smooth, its spin stayed invisible, its body remained quiet. So the silence itself became suspicious, because in space, stillness isn't passive. Stillness takes energy, stillness takes design, and 3I Atlas, against all mechanical logic, stayed still when nothing should have. Not like a comet, not like a rock, more like a satellite, awaiting its next signal. If light is the language of visibility in space, then electromagnetism is its deeper, more complex dialect, a language that reveals structure, interaction, and unseen behavior. And when 3I Atlas passed through perihelion on November 11th, 2025, it didn't just reflect light, it echoed something else entirely. Shortly after the brightness spike and the unexpected trajectory shift, a number of radio telescopes across Earth began to detect something strange. A series of faint structured pulses in the megahertz MHz range. These pulses were not part of any known solar emission. They didn't match flare activity, background plasma noise, or instrument artifacts. They came from a tight corridor in space, aligned precisely with 3I Atlas's outbound vector. At first, these signals were assumed to be part of the solar wind's natural noise. The sun produces an enormous electromagnetic signature at all times, especially during flare cycles. But a few key details set these pulses apart. First, they were short, lasting between 0.8 and 1.2 seconds each. Second, they were rhythmic, occurring at intervals of approximately 137 seconds. Third, and most critically, they were directional, only observed when dishes were trained within a tight beam arc around the object's coordinates. Individually, any one of these factors could be dismissed as coincidence or background activity, but all three, that caught attention. The low-frequency array, LOFAR in Europe, confirmed the signal within 45 minutes. The Allen Telescope Array in California picked it up just 10 minutes later. And a third confirmation came unexpectedly from the Ukrainian UTR-2 facility, which recorded two pulses at slightly different frequencies but with the same spacing. Independent confirmation across instruments, hemispheres, and detection technologies. That made the event real. But real what? The most conservative explanation was plasma interaction. As 3I Atlas passed through solar magnetic fields, perhaps it generated localized eddies in the charged particle stream. This could, in theory, produce emissions through cyclotron resonance, where electrons spiral along magnetic lines and emit at specific frequencies. But that phenomenon produces wide-spectrum noise, not narrow pulsed emissions. Others proposed that the object might have acted like a floating antenna, with conductive materials inducing weak emissions in response to solar wind oscillations. This would require the body to contain highly ordered metallic regions, surfaces capable of not just receiving, but momentarily storing and re-emitting electromagnetic energy. If true, that implies structure, not random composition, but conductive geometry. Further analysis revealed something more unsettling. The pulse intervals, 137 seconds, didn't match any natural solar rhythm. They didn't align with flare harmonics, plasma wave patterns, or known planetary influences. But they did mirror the timing of earlier anomalies, the brightness surge, the magnetic field ripple, and the onset of the trajectory deviation. Each pulse followed one of those events by the same time gap. This suggested not just synchronicity, but feedback. Like an echo. Radio astronomers were cautious. The word signal was deliberately avoided in official communications. But in private Slack channels and internal memos, terms like structured emissions, non-random spacing, and reactive coupling began to appear. No one claimed intent. No one used the word transmission, but they didn't need to, because the pattern already implied it. Adding further weight was the narrow-band nature of the pulses. Emissions centered around 3.2 mHz, with harmonic extensions reaching 6.4 and 9.6 mHz, ratios that follow a clear mathematical progression. Nature produces harmonics too, yes, but usually with broader, fuzzier footprints. These were clean. Then came the silence. After 4 pulses, the emission stopped. Completely. As if a cycle had completed, as if a system had reset. No subsequent pulses were recorded. No emissions reappeared. The spectrum flattened. And yet the memory of those pulses persisted. In data logs, in orbital records, in every simulation that now had to include a field interaction it couldn't account for. Because in the aftermath of the flare, the brightness, and the motion, 3i Atlas didn't just change direction. It spoke, briefly, quietly, on a wavelength we weren't expecting. And then it vanished back into radio silence. Of all the anomalies tied to 3i Atlas during its close solar approach, perhaps the most mechanically baffling was the way it emitted heat. Not broadly, not randomly, but in a specific direction. This phenomenon came to light only after cross-referencing thermal data from 3 different platforms: ESA's Solar Orbiter, NASA's Parker Solar Probe, and a narrow-angle radiometric array aboard JAXA's Hinode satellite. Each captured thermal profiles from different orbital vantage points as the object emerged from perihelion, and each reported the same strange conclusion. The infrared emission coming from 3i Atlas was not spherical, not even hemispherical, but anisotropic, meaning it radiated heat along a narrow corridor like a focused beam. This isn't how space objects behave. In normal conditions, when a body absorbs solar energy, that heat gradually diffuses across its surface. As it rotates, or even if it doesn't, its infrared radiation is distributed in every direction, with minor concentration toward the sunward side. This creates a classic blackbody emission profile, predictable and symmetrical, but 3i Atlas didn't follow this rule. Instead, it radiated warmth from a fixed offset vector, one that pointed away from the sun at a diagonal angle of approximately 42 degrees off-axis. This was not a brief anomaly. The directional emission persisted for more than 6 hours. And more curiously, the direction itself remained stable, even as the object's position in the solar system changed. That would suggest the heat was not being emitted in response to surface temperature, but from an internal control mechanism. Initially, scientists looked to known materials science. Could the object's surface be made of layered conductors, forcing energy to follow a guided path towards specific points? Could there be fissures or angled faces on the object that concentrated heat discharge? These possibilities were modelled. None fit the observed data. The emission was narrow-band and collimated, terms usually reserved for engineered thermal vents or radiators. In fact, the heat spread was so focused that it bore more resemblance to a spacecraft's thermal management system than a natural body. Spacecraft often use radiative panels to expel excess energy directionally, minimizing structural stress and preventing equipment damage. These systems are carefully angled and rely on materials with distinct emissive properties. No known comet or asteroid has ever exhibited a similar trait. No natural object in our catalogue controls heat this way. Moreover, the wavelength of the emission itself was oddly concentrated. Instead of emitting across a broad spectrum as a hot rock would, 3I Atlas radiated most strongly between 9 and 11 microns, a range associated with polished ceramics and composite metals, not the silicates or carbonaceous compounds typically found in interstellar fragments. The implications began to compound. This wasn't just thermal shielding, this was thermal targeting. The fact that the emission vector pointed away from the Sun, but not in direct opposition, further deepened the mystery. It suggested the object wasn't merely re-radiating solar energy, it was possibly using the Sun's heat as input, converting and redirecting it deliberately. Some researchers began comparing the data to thermophotovoltaic systems, solar collectors that convert heat to electricity and then expel excess energy through engineered vents. If 3I Atlas possessed such a system, it would represent a level of internal complexity never before seen in an interstellar body. It would also imply purpose. The final nail in the coffin came from a passive flyby sensor on the Parker Solar Probe, which caught the emissions fringe. The probe's magnetometers recorded a secondary wave in the plasma flow, a soft ripple consistent with a warm body disturbing the solar wind not broadly but in a line. The emission, in other words, didn't just release energy, it sculpted the environment around it, in silence, in precision, and in a direction no one could explain. By the time the heat signature faded, the object had already veered off course. The directed emission did not leave a trail. It left only a question. What kind of object manages heat like that? Deliberately, narrowly, and without any visible moving parts? Nature may be clever, but nature doesn't aim. Every comet, no matter how small, carries dust. It's the one universal trait shared across icy bodies that venture near the Sun. As surface material heats, ices vaporize and carry silicate particles, carbon-rich grains, and rocky fragments outward. These tiny solids reflect sunlight, scatter infrared radiation, and form the hazy, glowing coma that defines a comet's character. Even asteroids that are only partially volatile leave faint dust trails as they pass through intense solar energy. But 3I Atlas did none of that. Despite passing through the most intense heating zone of its orbit on November 11, 2025, within the solar thermal radius where sublimation is virtually guaranteed, no coma formed. And more disturbingly, no dust signature was detected at all. This wasn't just a curiosity, it was a contradiction. Dust is usually the first thing telescopes detect. Instruments like the Wide Field Infrared Survey Explorer, WISE, and James Webb Space Telescope, JWST, are designed to spot particulate backscatter in the near-infrared, even when gas emissions are too faint to measure. And during its approach, 3I Atlas was watched by a coordinated array of systems across 3 continents and 2 orbital observatories. Yet the object remained optically clean. Spectrometers trained on its location found no excess absorption lines in the 9 to 12 micron range, lines normally associated with silicates, alumina, or carbonaceous dust. The data was razor flat. Instead of scattering sunlight or glowing with particle heat, the space around 3I Atlas remained black. This absence confused scientists more than a sudden flare would have, because for an object of its brightness and trajectory, some amount of particle shedding should have been inevitable. Even if it were not a true comet, even if it were rocky, tiny micrometeorite impacts, solar radiation pressure, and thermal expansion should have stripped at least trace material from its surface. But even SOHO's LASCO C3 coronagraph, which can detect micron-sized dust through reflected sunlight near the Sun's corona, recorded nothing. Some proposed that perhaps the object had already lost its volatile outer layers before entering the inner solar system. But that was inconsistent with the brightening event it exhibited near perihelion. A brightness increase implies a change in surface or environmental conditions, usually involving ejected material. But 3I Atlas's light curve spiked without any accompanying particulate field. Even more telling was its wake. After perihelion, as the object began its outbound journey, researchers turned to backlit imaging techniques to search for trailing particles. The Sun provided a perfect silhouette opportunity. Had there been even a minimal dust trail, backscatter should have revealed it. But there was no visible streak, no diffusion cone, no scattering gradient, just an object, alone. This led to a deeper hypothesis, that either 3I Atlas never had a dust-bearing surface to begin with, or something was actively preventing its release. Some compared the situation to interstellar asteroid Oumuamua, which had also shown signs of non-gravitational acceleration without an observable dust trail. But 3i Atlas went further. It didn't just avoid shedding particles, it absorbed or deflected any mechanism that would produce them. This suggested either a uniquely cohesive structure or a protective layer strong enough to withstand thermal expansion and radiation pressure. The lack of dust also destroyed traditional mass estimation models. Normally, scientists infer an object's size and density by measuring both its reflective surface and its particulate cloud. Without dust, only the core remained, clean, bright, and inexplicable. This rendered 3i Atlas an enigma in terms of its physical composition. Was it metal, ceramic, something else? Adding to the puzzle was the behavior of nearby solar particles. In a typical comet event, the released dust influences the solar wind, creating perturbations and shifts in local particle density. But when the Parker Solar Probe crossed 3i Atlas's path 48 minutes after its closest approach, its sensors found no particulate turbulence, no charged debris, not even micron-sized grains, just clean plasma. In the silent vacuum of space, dust is a comet's voice. And in the case of 3i Atlas, there was no whisper, no breath, no trail, only silence. Among the many methods astronomers use to understand distant objects, light polarization remains one of the most subtle and most revealing. When sunlight bounces off the surface of a comet, asteroid, or planet, it becomes partially polarized, depending on the material, texture, and angle of reflection. By analyzing these polarization patterns, scientists can deduce not just composition, but even microstructure, grain size, surface roughness, and layering. But in the case of 3i Atlas, polarization didn't behave the way it should have. It reversed. In the hours surrounding perihelion on November 11, 2025, 3 different observatories, the Very Large Telescope in Chile, the Subaru Telescope in Hawaii, and the Indian Astronomical Polarization Array, all reported something extraordinary. At a solar phase angle of approximately 38 degrees, the object exhibited negative polarization. That in itself is rare, but not unheard of. Small particles can produce negative polarization at low phase angles. The shock came 2 hours later. As 3i Atlas moved away from the Sun and the phase angle increased, the polarization vector flipped. Not gradually, not like the smooth inversion we see in dusty comets, but suddenly. Within a 12-minute window, the direction of polarization jumped nearly 90 degrees, completely inverting the light's electric field orientation. That is not natural behavior. In typical solar system bodies, polarization shifts are caused by physical processes, phase angle geometry, light scattering off irregular particles, or wavelength-dependent interference. But those shifts are gradual, slopes in a smooth curve. What happened with 3i Atlas was a step function, a discrete jump, not a transition. This caught researchers completely off guard. Polarimetric readings showed a sharp decline in degree of polarization, followed by a total sign change. Simultaneously, a narrow band spike in the blue-green wavelength range, around 520 to 540 nanometers, indicated a possible coherent scattering event, meaning the surface, or the object's near-field structure, briefly acted like a diffraction grating or a photonic layer. This suggests ordered surface structures on a scale smaller than the wavelength of light, something common in engineered materials, but unknown in natural space bodies. Some theorists propose that the polarization reversal could be caused by a layered refractive interface, a thin transparent surface like fused glass or crystal that briefly shifted its optical alignment. Others suggested a form of electro-optic response, where the material's internal structure changed under influence of the solar electromagnetic field, like an adaptive lens. Either way, the data pointed toward one conclusion: polarization was being influenced, not merely caused. A further oddity emerged in timing. The polarization flip occurred within seconds of the heat emission vector reorienting, as recorded by the Parker Solar Probe, and confirmed through solar wake analysis. That synchronicity suggested the two events were not isolated. If heat was being expelled in a specific direction, and polarized light suddenly reversed orientation at the same time, the implication was that the object's optical properties were being dynamically controlled. This has never been observed in a comet, asteroid, or natural satellite. What made it even stranger was that the polarization returned to its original orientation an hour later. not symmetrically but slightly offset by 11 degrees. This asymmetry, combined with the abrupt shift, destroyed the idea that it was caused by rotation or passive surface behavior. Something had actively modulated the light. In practical terms, this reversal broke one of the few constants astronomers rely on. Light should behave predictably, and yet here was an object that didn't just reflect or emit. It altered light behavior mid-transit, as if reacting to a threshold, an internal clock, or an external signal. Some researchers began comparing the event to liquid crystal displays or electrochromic panels, materials that reconfigure their molecular structure to redirect light based on voltage or environment. If anything even remotely similar was occurring on 3I Atlas, it would mean the surface wasn't inert. It was responsive, and in the language of astrophysics, a responsive surface implies a design, something that watches the sun and changes how it is seen. In astronomy, reflectivity or albedo is typically a fixed property. It's a passive trait, determined by an object's surface material, texture, and angle relative to the sun. Dusty comets have low albedo, reflecting just a small fraction of the light they receive. Metallic asteroids reflect more, but even they remain stable across time. So when 3I Atlas demonstrated modulating reflectivity, scientists immediately knew something was different. On November 11, 2025, just after its perihelion, the object experienced what has now been referred to in internal reports as the brightness pulse. This was not a single event, it was a sequence. Using synchronized data from NASA's Solar Dynamics Observatory, SDO, the European Southern Observatory, and the James Webb Space Telescope, researchers observed 5 distinct surges in visible reflectivity. Each lasted between 22 and 35 seconds, followed by intervals of darkness. These fluctuations were not due to flare activity from the sun. Solar output remained constant throughout the observation window. Nor were they due to rotation, which had already been ruled out by light curve analysis. This left one conclusion. 3I Atlas was altering how it reflected light, actively. The first surge peaked at an albedo equivalent of 0.73, rivaling that of fresh snow or polished ice. Then, within seconds, the reflectivity dropped below 0.18, darker than charcoal. These values are not just far apart, they're mechanically incompatible on a static surface. Something had to be changing in real time. Initially, skeptics proposed that these were instrument artifacts, perhaps due to angle shifts or solar interference, but the synchronized timestamps across 3 independent systems invalidated that. The brightness pulses were real, timed, and repeatable. Further complicating the picture was the spectral consistency of the reflection. While the intensity changed drastically, the wavelength signature remained stable, centered tightly in the visible band. This eliminated the possibility of flaring gases or heated particles, which tend to shift emission toward the infrared. What changed was only the brightness, not the color. This led to a stunning hypothesis: surface modulation. In material science, there are substances known as electrochromic materials, films that change reflectivity when exposed to electrical currents or voltage changes. They're used in smart windows, adaptive camouflage, and some satellite components. Could a similar principle be at play on the surface of 3I Atlas? If so, it would imply that the object wasn't just passively reflecting sunlight, it was controlling its optical cross-section, essentially deciding how much of itself to reveal at any given moment. This would not only explain the dramatic albedo shifts, but it could also clarify why the object vanished in certain observations. For example, the Chinese Chang'e Deep Space Radar recorded a complete loss of radar echo during one of the dim phases. It wasn't just less reflective in visible light, it was absorbing or redirecting all incoming signals. Even more provocative were the pulse intervals. They occurred roughly every 142 seconds, which echoed the earlier electromagnetic pulse pattern recorded after perihelion. These repeating sequences began to resemble a programmed cadence more than environmental chaos. To test this idea, simulation labs at Caltech and the Max Planck Institute recreated reflectivity profiles using advanced photonic crystals, materials engineered to manipulate light flow at the nanoscale. With extreme fine-tuning, they were able to reproduce similar modulation patterns, but only under controlled laboratory conditions. 3I Atlas was doing it in deep space. The implications of this cannot be overstated. No natural process can cause high-frequency reflectivity modulation at these magnitudes, with such precision and across multiple observation points. This wasn't outgassing, this wasn't tumbling, this was visibility control. The final clue came from polarized light experiments, which showed that during the brightest phase, light was scattered diffusely, as if from a smooth mirrored surface. During the dim phase, scattering vanished almost entirely. The surface, it seemed, could switch textures optically. And that kind of adaptive reflectivity isn't something rocks do, it's something machines do, or something built to hide and reveal itself at will. Every comet in recorded history has obeyed one simple, reliable law. Its tail always points away from the sun. This rule isn't about the direction the comet is moving. It's about solar radiation pressure and the solar wind, streams of charged particles and photons constantly emanating from the sun. These forces strike dust and gas emitted by a comet and push them outward, forming the characteristic bright tail that stretches into space, opposite the sun. It's the most visually iconic feature of a comet, and perhaps its most predictable. So when 3I Atlas passed perihelion, on the morning of November 11, 2025, and a thin tail was observed, but not in the direction expected, astronomers worldwide paused. Then they double-checked. And then, for many, came a cold realization. The tail was pointing the wrong way. Initial imaging came from the Solar Orbiter's heliospheric imager, which captured a faint but measurable plume of material beginning to emerge approximately 17 minutes after the object's closest approach to the Sun. Instead of trailing away from the solar vector, the tail projected forward, angled nearly 28 degrees ahead of its orbital path, and crucially, toward the Sun. This configuration made no physical sense. The entire foundation of tail formation rests on outward pressure. It's how dust gets swept into space. It's how plasma tails form and stretch for millions of kilometers. A forward-pointing tail would require the material to be actively accelerated against the solar wind, a violation of basic conservation principles. The first suggestion was optical illusion. Perhaps it was a projection artifact, a trick of perspective from one observation angle. But then came confirmation from Earth-based coronagraphs in South America, the Indian Institute of Astrophysics, and ESA's sun-watching satellite Proba 2. All three showed the same thing, a tail not repelled from the sun, but arcing forward and slightly downward, like a jet. And it held position for nearly 2 hours. During that period, the object continued its outbound course, and the tail slowly faded. Spectral analysis of the plume revealed it lacked typical ionized oxygen or carbon lines. Instead, it showed a narrow emission around 630 nanometers, a red-orange wavelength not commonly dominant in cometary gas. This suggested a different chemical composition or more radically non-chemical emission, possibly thermal particles or engineered particulates. One team proposed a gas-venting model. Perhaps 3I Atlas had a buried volatile reservoir that erupted, directing outflow forward like a geyser. But simulations show that even extreme internal pressure couldn't overcome the counterforce of the solar wind to produce a stable, forward-angled jet. The event raised another disturbing question. Was this tail intentional? Because if the object was emitting material or energy forward, it wasn't shedding mass. It was possibly steering. Theoretical propulsion methods, such as solar mass drivers, have been studied in advanced propulsion labs. These systems expel particles or energy against environmental forces, trading momentum for velocity control. If 3I Atlas were using any such method, even at microthrust levels, it would explain both the trajectory deviations and the peculiar tail orientation. The tail itself behaved unlike any known debris stream. It remained narrow, almost collimated, with minimal dispersion. Its brightness did not decay exponentially, as would be expected from sunlight diffusion through expanding particles. Instead, the brightness tapered linearly, suggesting either an ongoing emission or guided flow. One final twist came from an unexpected source, the Goldstone Solar System radar. While bouncing signals off 3I Atlas's path, it recorded a frequency distortion that aligned not with the object's core, but with the tail. In other words, the tail was reflective, or at least responsive, to high-frequency input. This raised the possibility that the tail wasn't a tail at all. Maybe it was an exhaust, or a signal, or something no one had a word for yet. But whatever it was, it defied gravity, pressure, and light. It pointed not away from the sun, but toward something else, and in that moment the solar system's most basic visual rule was broken. Not bent, not twisted, broken. For centuries, scientists have understood that space is not empty. It's woven with magnetic fields, flowing currents of charged particles, and delicate structures shaped by solar wind and interplanetary plasma. Most celestial objects, comets, asteroids, planets, interact with these magnetic streams in passive, predictable ways. But during the observation of 3 Atlas near the Sun on November 11, 2025, instruments recorded something that turned that passive model on its head. The object appeared to be surrounded by a magnetized envelope, a coherent, structured magnetic field that deflected incoming particles far beyond what its size would allow. This discovery was first hinted at by anomalies in solar wind data coming from NASA's Parker Solar Probe, which flew through the object's outbound path just under 2 hours after its perihelion. Researchers expected turbulence, a disrupted flow of ions trailing behind a fast-moving interstellar object. Instead, they found a clean void, a region where the solar wind had been diverted, smoothed, and rerouted, as though it had passed around a powerful magnetic shell. This shell was far too large to be natural. Modelling the flow revealed that the deflection zone stretched over 700 kilometres from the object in all directions, an impossibly large magnetosphere for a body estimated to be under 200 metres wide. Natural magnetic fields on such small objects are weak, fragmented, and inconsistent. Even the strongest remnant magnetism on iron-rich asteroids barely registers beyond a few metres from the surface. But the Parker data showed a smooth gradient. The field strength increased steadily as the probe approached the projected position of 3I Atlas, then dropped off rapidly once it passed through the boundary. It looked artificial. The term magnetized envelope quickly emerged among researchers. Some suggested the field could be a form of plasma sheath, created by the interaction of ionized gases surrounding the object. But that theory collapsed when the solar orbiter's instruments, particularly its ultraviolet spectrometer, found no evidence of plasma particles in that region. No ion tail, no coma, no gas cloud, just magnetism hanging in place. This led to a more radical proposal, that 3I Atlas carried an internal magnetic field generator, a deliberate system creating a controlled electromagnetic barrier. This idea, while extreme, matched the data perfectly. If the object was enveloped in a stabilized magnetic bubble, it would explain several of its other anomalies: the absence of dust, the lack of visible outgassing, the directional heat emission. Even the trajectory deviations could be partially attributed to magneto-hydrodynamic interactions with the solar wind, effectively using the sun's own plasma to create gentle steering forces. But such a system would require real-time feedback control. The object would need to sense incoming solar particles, adjust its field accordingly, and maintain a coherent envelope under constantly changing solar conditions. This is not just complex, it's beyond the capability of any known spacecraft operating today. And yet, there it was. The final confirmation came from data collected by the Interplanetary Monitoring Platform 3, which detected a low-frequency magnetic oscillation within the envelope itself, pulsing at 0.7 Hz like a heartbeat. This signal was too regular to be a natural resonance and showed no harmonic relation to nearby solar cycles. Instead, it suggested internal structure, a controlled pulse, a system at work. Some observers liken the envelope to a magnetic cocoon, shielding the object from thermal and particle damage as it pierced the sun's outer environment. Others began comparing it to theoretical plasma sails, magnetized fields designed to surf on solar wind pressure without deploying physical structures, but the difference was in the scale. 3I Atlas wasn't deploying a sail, it was the sail. Wrapped in invisible magnetism, untouched by heat, silent against the solar wind, it moved through space as if designed to withstand something our instruments could barely sense. And that's when the magnetized envelope hypothesis stopped being speculation. It became the only explanation that fit the data, because no rock deflects the solar wind like that, no comet carries a heartbeat in its field, and nothing natural wears a shield. Unless it knows, it needs one. On the surface, 3I Atlas was quiet. No visible tail, no rotation, no dust. But when researchers began analysing the radiospectrometry data from its perihelion pass on November 11th, 2025, they found something hidden beneath that silence, a standing wave. It wasn't a sound, and it wasn't light. It was a persistent low-frequency oscillation embedded in the radio background, locked in place like an invisible scaffold around the object. This type of phenomenon had never been recorded from a comet, asteroid, or interstellar body, and yet multiple instruments picked it up simultaneously, from the Jodrell Bank Observatory in the UK to the Deep Space Network antenna in Canberra to the FAST telescope in China. Each telescope, using different radio windows, independently reported a narrow band signal oscillating around 1.44 GHz. But the key detail wasn't just the frequency, it was the waveform. Instead of behaving like a moving wave, travelling, decaying, spreading, the signal showed characteristics of a standing wave. In physics, a standing wave occurs when two waves of the same frequency and amplitude interact in such a way that they cancel out movement, creating stationary nodes and antinodes, fixed points of silence and resonance. These patterns are common in engineered environments, in antenna chambers, resonance boxes, and tuned cavities, but they are nearly impossible in open space. The only way a standing wave can persist in vacuum is if it is being sustained, either trapped between two boundaries or actively regenerated. In the case of 3i Atlas, there were no external reflectors, no companion body, no containment field. The signal was originating and terminating at the same location, the object itself. This discovery stunned the scientific community. Space is filled with noise, cosmic microwave background, solar flare activity, Jupiters, radio emissions, the hiss of interstellar hydrogen. But a structured wave repeating at fixed intervals with no Doppler drift implied coherence, and coherence implies organization. Researchers began asking a new question. Was the wave a byproduct of the object's internal structure? Or was it a kind of carrier signal, like those used in communication systems? The frequency itself, 1.44 GHz, sat awkwardly close to the standard L-band used for spacecraft telemetry, radar, and some satellite communications, but it was offset just enough to avoid known human-made transmissions. This raised the suspicion that the wave was not just being emitted, but was meant not to interfere, a shadow signal, deliberate but discrete. To test the structure, the VLA, Very Large Array, ran a high-resolution phase mapping sequence across the wave. What they found added fuel to the mystery. The standing wave was modulating in amplitude every 4.7 seconds. Subtle changes, like a breath. Not enough to encode data in any known format, but too regular to be environmental. One proposal from a team at MIT's Haystack Observatory suggested that the wave was caused by internal resonance, that 3i Atlas housed a cavity or chamber reflecting electromagnetic energy within itself. That would require internal geometry, conductive walls, and a power source. No known natural body can sustain that kind of architecture without disintegrating under solar stress. Others suggested it was an artifact of detection, interference from Earth, harmonics from passing satellites. But then came confirmation from the Voyager 2 probe, over 20 billion kilometers away. It picked up the same wave, at the same frequency, aligned with the object's position relative to the Sun. That ruled out Earth-based noise. In deep space engineering, standing waves can be used as resonant buffers, communication nodes, or field stabilizers. All three require purpose. All three require design. The fact that this standing wave held steady for nearly 6 hours, through perihelion heat, solar wind pressure, and intense radiation, meant it wasn't fragile. It was resilient. And as 3i Atlas moved on, the signal faded slowly, as if powered down rather than dispersed. Some dared to say what others wouldn't. This wasn't just an anomaly, it was a signature, a sign that the object, despite its silence, was doing something active, not just reflecting sunlight, but broadcasting its presence in a language no one had ever heard before. Or perhaps, a language we'd simply forgotten how to listen to. One of the simplest ways to understand the behavior of any celestial object is by measuring its light. More specifically, by analyzing the temperature of that light. Stars, comets, and even icy moons emit light based on how hot they are. The hotter the surface, the more energetic the photons, and the clearer the relationship becomes between temperature and emission. This is known as black body radiation, but on November 11, 2025, During the perihelion flyby of 3I Atlas, that relationship broke. The object was emitting light, but not from heat. This baffling observation was first noted by the Infrared Telescope Facility, IRTF, in Hawaii, and later confirmed by ESA's Infrared Spectral Mapper, which had been assigned to track the object's thermal signature as it grazed the Sun. Expectations were clear. As 3I Atlas entered the region of peak solar heating, its surface should warm and the infrared emission should spike accordingly. And it did, but only for a moment. For exactly 6 minutes, the object behaved as expected. Surface temperature climbed from an estimated 90 Kelvin to over 340 Kelvin, and the infrared glow increased accordingly. But then, the emission profile diverged from thermal logic. The object cooled, yet its visible light output continued to rise. This was not just strange, it was impossible under classical physics. In simple terms, the object was getting dimmer in the infrared, while simultaneously getting brighter in visible light. The only way to explain this was if the light being emitted was not thermal in nature. In other words, the photons weren't the result of heat, but of some other process. That process, researchers now believe, was non-thermal emission, a category that includes fluorescence, electroluminescence, and coherent light generation like lasers. Several characteristics of the light pointed in that direction. First, the spectrum was unusually narrow. Most heated bodies emit across a broad range of wavelengths, forming smooth curves. But 3I Atlas's visible light was spiked, intense at 505 nanometers and virtually silent elsewhere. That's not how heated rock behaves. That's how excited electrons behave when they drop energy levels in a controlled way. Second, the light was directional. Observatories located in Chile, India, and aboard the solar orbiter reported different brightness levels at the exact same timestamp, despite being equidistant. This suggested the light wasn't being emitted equally in all directions, a key signature of structured emission, often associated with engineered light sources. Third, the emission pulsed. Faintly, but rhythmically. Every 9.3 seconds, the brightness shifted by about 2.7%, like a heartbeat. This was outside the range of any known rotation-based modulation, and didn't match any natural oscillation observed in other interstellar objects. Even more troubling was the lack of decay. Non-thermal emission in comets typically comes from volatile compounds fluorescing under solar radiation. These effects are short-lived and degrade quickly as material disperses, but 3I Atlas's light stayed consistent for nearly 47 minutes, with no change in spectrum or coherence. This forced astronomers to ask an uncomfortable question. Was the light being generated, not released? One proposed theory was surface-level electroluminescence, a phenomenon where electrical charges excite a material, causing it to emit light without heating up. It's used in everything from OLED screens to lab lasers, but in deep space, far from any external power grid, this raised a new mystery. Where was the power source? Another theory, even more radical, involved quantum coherence, the idea that electrons inside a structured lattice could move in phase, producing synchronized light waves. This effect requires extremely precise control of atomic structure, something only known in laboratory environments. If 3I Atlas was doing anything even remotely similar, it would suggest not just composition, but engineering. The implications are profound. Light is one of the few constants in the cosmos. Its behavior has guided astronomy for centuries. And yet here was an object that rejected the thermodynamic rules. It didn't burn, it didn't smolder, it glowed by choice, not by temperature. It didn't reveal itself through heat. It chose another way to be seen. Of all the chemical signatures astronomers expected to find near 3I Atlas, nickel carbonyl was not on the list. This molecule, nicowat, is incredibly rare in nature. It forms only under very specific conditions: a low-pressure environment, the presence of carbon monoxide gas, and trace amounts of elemental nickel. It's volatile, highly toxic, and breaks apart easily when exposed to ultraviolet light. It is also extremely unstable in space. And yet, on November 11, 2025, shortly after perihelion, spectrometers from both the James Webb Space Telescope, JWST, and the Chinese Tianwen Deep Space Surveyor detected unmistakable traces of nickel carbonyl surrounding the object. This discovery made no sense. Comets and interstellar objects often contain a variety of simple compounds: water vapor, carbon dioxide, methane, and even traces of more complex hydrocarbons. These are the leftovers of early star formation, frozen remnants of cosmic dust. But nickel carbonyl is synthetic in origin on Earth. It was first discovered in the 19th century in industrial laboratories, and today it is used in metal refining, nanomaterial synthesis, and as a precursor in the production of high-purity nickel. To form nickel carbonyl in space, two conditions must be met simultaneously. Metallic nickel must be exposed to gaseous carbon monoxide. The environment must be cool and shielded enough to prevent ultraviolet disintegration. The surface of 3I Atlas, according to every thermal map we have, did not meet either requirement. Its nickel content was already considered anomalous. The early reflectance spectra showed stronger metal signals than most rocky comets, but this went further. The presence of Ningaya 4 implied a chambered reaction, something shielding these molecules from solar radiation and allowing them to accumulate in measurable quantities. That's not a coincidence, that's a process. The spectral traces were subtle but consistent. Emission lines appeared at 2050 and 2200 centiatm/1, characteristic of the carbonyl group's stretching vibration. These readings were cross-verified using both infrared absorption data and microwave line tracking, confirming that what we were seeing wasn't dust contamination or sensor error. It was a real, localized chemical signature. The next question was, why would an object like this produce nickel carbonyl at all? The leading theory came from a group at the Max Planck Institute for Extraterrestrial Physics, who noted that NiCO4 is uniquely suited for thermal decomposition into pure nickel. In industrial processes, it is used precisely because it breaks down at relatively low temperatures, depositing fine layers of nickel onto surfaces. If 3I Atlas were utilizing a similar principle, whether naturally or otherwise, it might suggest a form of self-repairing surface behavior, in which volatile compounds cycle over a structure and reinforce it during solar exposure. In this model, the object isn't a rock, it's a maintained system. Other researchers speculated that the molecule could be a byproduct of engineered cooling systems. Because nickel carbonyl absorbs solar radiation efficiently and breaks down into reflective material, it could act as a kind of light-activated thermal buffer, a chemical that cools the surface while also depositing protective layers. But the most disturbing possibility came from data correlation. Shortly after the strongest nickel carbonyl signatures were detected, the same region of space exhibited a temporary radar opacity. For 37 seconds, JAXA's Hayabusa L radar array failed to detect any return signal from 3I Atlas. The object had not vanished, it had become transparent to radar. Nickel carbonyl, in gaseous form, is known to scatter and absorb certain frequencies, particularly in the X-band used for deep space communication. This raised a new hypothesis. The gas wasn't a byproduct, it was camouflage. Whether intentional or incidental, the presence of nickel carbonyl had the effect of blinding high-frequency sensors and masking structural signatures, creating a chemical fog that prevented detailed scans. In practical terms, this meant 3I Atlas could cloak portions of itself, or at the very least reduce detectability. And that's not the behavior of a comet. That's the behavior of something that doesn't want to be seen. Or, perhaps more precisely, only wants to be seen on its own terms. Every known object in space spins. From the smallest asteroid to the largest planet, rotation is a fundamental consequence of motion and formation. Whether caused by the conservation of angular momentum from the solar system's birth or by past collisions, spin is everywhere. It's so universal that astronomers use it to estimate mass, shape, and structural integrity. But on November 11, 2025, when 3I Atlas passed its closest point to the Sun, something strange was confirmed. It wasn't rotating. Not at all. This wasn't just a temporary pause or a slowed spin from tidal forces. It was a complete and persistent absence of measurable rotation, lasting for over 9 consecutive hours, and confirmed by at least 5 independent observation platforms, including the Solar Dynamics Observatory, SDO, Goldstone Radar, ESA's Probe 2, and the Very Large Telescope, VLT. Normally, rotation is detected through light curve analysis, by measuring how an object's brightness changes over time. As irregularly shaped bodies spin, the amount of reflected sunlight changes rhythmically, like a lighthouse beam. But with 3I Atlas, the light curve was flat, perfectly flat. Not a hint of oscillation, not even from minor albedo variations that would suggest surface unevenness. This alone was unusual, but it became even more significant when radar imaging confirmed that the object maintained a constant orientation relative to the Sun. Over hours of observation, its leading edge remained fixed, like a spacecraft keeping its solar panels aligned. For a natural object, this is virtually impossible. Objects without active stabilization eventually tumble, especially when approaching a massive gravitational body like the Sun. Comets often spin up or down near perihelion as sublimating gases apply torque. Even spacecraft require thrusters or reaction wheels to maintain this kind of attitude control. So how was 3I Atlas holding position? Some scientists proposed that it was rotating, but along its axis of symmetry, making it appear still from our perspective. But this theory collapsed under the multi-angle data from space-based sensors. Different viewing angles should have revealed subtle shifts. None did. No matter where it was observed from, the object's profile remained unchanging. Another theory involved mass damping, a natural phenomenon where internal material shifts cancel out rotational momentum. This effect, seen in some rubble pile asteroids, can cause a slow reduction in spin. But even in those cases, a faint wobble remains. With 3I Atlas, there was no precession, no libration, no movement at all. Eventually, a more radical hypothesis emerged, that 3I Atlas was using active stabilization, possibly through internal gyroscopic systems or microthrust adjustments. If true, this would mean the object was capable of real-time orientation control, similar to how Earth satellites or telescopes maintain pointing accuracy. This theory gained traction after radiometric anomalies were detected on the object's sun-facing side. Instruments aboard the solar orbiter found fluctuating infrared microbursts, too localized to be natural flares and too short-lived to be thermal echoes. These bursts occurred at regular intervals, once every 6.2 seconds, always on the same part of the object. This pattern suggested attitude maintenance, small directional heat, or energy emissions counteracting rotational drift. Essentially, it was performing the equivalent of spacecraft yaw correction, without visibly moving. Then came the final piece of evidence. The Jodrell Bank Observatory detected phase-locked electromagnetic pulses coming from the object, synchronized with solar wind variations. These pulses were offset in time just enough to suggest predictive correction, not reaction, but anticipation. The object was responding to forces before they arrived, as if guided by an internal model of its environment. In essence, 3I Atlas wasn't spinning because it was choosing not to spin. This behavior runs contrary to every natural celestial mechanic we've observed. It implies real-time data processing, structural integrity, and energy expenditure, all hallmarks of an engineered system. The implications are unsettling. Because in space, stillness is never passive. Stillness is intentional. And 3I Atlas held its orientation not out of chaos, but out of control.